Hi everyone, my name is Matt Schallert. I'm a site reliability engineer at Uber and really excited to be here today to share with you some of our experience in scaling and automating some of our systems over the past few years, specifically some of those stateful systems of ours and building on automation on top of Kubernetes. A little bit about myself. Like I said, I'm a site reliability engineer at Uber. I've been there for just under 3 years now, and the entire time I've been working on M3, which is Uber's in-house and open source metrics platform. Some of what we're going to cover today, just to start off, give you the background and context of the history of the metric system at Uber, talk about some of the scaling challenges that we ran into with it, how we went about solving those challenges using automation, and specifically how we automated those workloads, or some of our workloads using Kubernetes. So a little bit of history about the metric stack at Uber. Back in 2015, this is what Uber's metric stack looked like. So there were servers in our data centers. These servers ran processes. These processes emitted metrics to a local metrics daemon that would take care of flushing metrics through the system. And eventually metrics were raw time series data was stored in Cassandra, and metrics were indexed in Elasticsearch to allow for things like path-based or tag-based queries. But by 2016, Uber had grew pretty rapidly, and so had the usage of the metric stack, and the team found themselves in a difficult situation with Cassandra. Cassandra had become a source of instability in the system, and there was a lot of time just spent kind of operating it and trying to keep it healthy. Additionally, we were throwing a lot of expensive hardware at Cassandra to try to help keep up with the load. But I should say this isn't necessarily a problem with Cassandra, but more that we were using it for a pretty pathological use case of just storing trillions of timestamp value pairs. So like I said, we were facing some operational issues. Cassandra had scaled well for our needs over the past year or two, but there were the human operational cost of, we were managing these clusters in config. We would sometimes run into split brain scenarios with our clusters where you would have to run node tool on a variety of hosts to kind of narrow down the source of the split brain. And also sometimes fixing things like a failed node join could require restarting a host that was stuck or something. And it was also, like I said, inefficient just in terms of how much hardware we were throwing at it. And we knew that Uber wasn't going to stop growing, so we needed a solution that would scale with us while requiring less maintenance overhead. And in response to these challenges, the team built M3DB, which is Uber's open source distributed time series database. M3DB is a time series database that we built with the real-time metrics use case in mind, although we've later expanded it to a variety of more generic use cases. But for that real-time metrics use case, M3DB uses a variant of Facebook's Gorilla time series encoding algorithm to give us roughly an 11 times compression ratio as opposed to just storing raw timestamp value pairs on disk. Since we optimize for real-time metrics data, we can avoid compactions in the common case since metrics are kind of just being written as they come in, which makes M3DB really fast. And to provide horizontal scalability, M3DB is sharded, and to provide fault tolerance, these shards are replicated across configurable failure domains, whether that be availability zones in a cloud region or racks in a data center. And we first deployed M3DB at Uber in late 2016. And compared to our Cassandra-based stack, we had a few benefits. We were able to really greatly reduce the operational overhead, and we'll see some of the methods that we use to do so. We were able to run M3DB on commodity hardware, so pretty much anything with a solid-state disk was good enough for us. And compared to some of the gossip split brain issues that we ran into with Cassandra, with M3DB, we have strongly consistent cluster membership backed by etcd. And to accomplish this, we use some libraries called M3 cluster. So M3 cluster is a set of cluster management libraries that we originally created for M3DB, but we kind of designed to be extensible to more of our workloads. M3 cluster contains ways of representing cluster topologies as well as libraries for manipulating them. So things like algorithms for efficiently distributing shards across a variety of failure domains in accordance to things like instance weight. It also contains common methods of service discovery, so tasks for discovering the other members of a cluster, dependencies, announcing one zone membership, runtime configuration for changing application behavior on the fly, and leader election for consumers that may need it. M3 cluster uses etcd for storing all of this data. So pretty much users of M3 cluster just have to be able to talk to etcd to perform all of these tasks. And if you're not familiar with etcd, it's a strongly consistent key value store similar to something like Zookeeper. You might also be familiar with Apache Helix, which is another set of open source cluster management libraries. M3 Cluster shares a lot of similarities with Apache Helix, but Apache Helix is pretty heavily cemented in Java land, and we were building this in a Go-based stack. So we wanted something that kind of more tightly integrated with our needs. The way that we represent these cluster topologies in M3DB is as desired states that the M3DB nodes work to converge on. So more concretely, here's what one of these cluster topologies looks like. The cluster topologies in M3 cluster are called a placement. Placement has some metadata associated with it, such as the replication factor and the number of shards. But more importantly, a placement contains a set of instances. Instances themselves have some metadata, such as their weight. So maybe for a disk capacity bound workload, you can weight on disk size, or for a CPU bound workload, you can weight on number of cores. But instances own shards, which represent some subset of the workload. One thing that was really nice for us about the weighting was that it allowed us to have non-homogeneous hardware in our clusters. This was an issue that we ran into in Uber's on-prem environments where new SKUs would sometimes come in, maybe they varied slightly from old hardware, and you kind of helped us treat them as just more resources in this pool rather than having to worry about specific instance types. So by 2016, here's what Uber's metric stack looked like. Pretty much these many Cassandra clusters were replaced with fewer but larger M3DB clusters. And deploying M3DB was a huge step for us. We were able to solve our most pressing operational issue by replacing our usage of Cassandra. We were able to make the system more reliable and faster for our users, which is always our top priority, all while reducing costs. But there was still a high operational overhead when it came to maintaining the system as a whole, and that mostly boiled down to one reason. And that reason was that we had greatly fragmented representation of the various components in our system. And I'll show you what I mean by that. So if you remember, we have these backend tiers that metrics would flow through after the collectors emitted them. But those backend tiers were actually comprised of a few parts. So first, metrics were emitted from these host local collectors and sent to a statsite tier for aggregation. The collectors discovered these statsite instances using Uber's internal runtime configuration service. But this was a runtime configuration service that was built more for product level use cases and not necessarily infrastructure daemon level configuration, which kind of brought a variety of problems. These statsite instances would then emit these aggregated metrics to the shunt tier, and they discovered the shunts through statically configured lists that were deployed with Puppet. Additionally, the collectors also had to be aware of these shunts if they were sending using a legacy emission format. So the collectors also had to discover these shunts through these statically configured lists that were deployed with Puppet. Then the shunt tier was responsible for routing and reflecting these metrics to the downstream indexers and ingesters. And the shunts would discover these tiers through static lists that were coupled with service builds and deploys. Then the M3DB ingesters would discover the M3DB clusters using M3 cluster, which we talked a little bit about, and we can ignore Elasticsearch for these purposes. But in summary, we had these systems represented in all these different ways, represented and discovered using Uber's internal runtime configuration service that was built for a completely different use case, some as statically configured lists that were deployed with Puppet, some as statically configured lists that were coupled with service deploys and would require rebuilding and redeploying a service to change, and then these M3DB placements that we've seen a little bit of so far. And this fragmentation had a lot of really painful implications that we were feeling on a daily basis. For one, it felt like we had these smaller, unrelated components rather than having one way to think about the system as a whole. And this made it really difficult to reason about the entire stack. So replacing a single host might involve a code change and then a coordinated build and deploy of multiple services. So it wasn't totally clear what would be impacted by any single change. And additionally, it was kind of difficult to reason about where you might have to make a change in order to impact the system. And all of this made onboarding new members to the team really painful because there was this crazy complex mental model that they had to keep in their head. And this also made it really difficult to automate all of these operations. So automating the process of making a configuration diff, rebuilding and redeploying some number of instances or some number of services in a particular order is really difficult, and if nothing else, probably a really bad idea, because it seems like there's a lot of ways that can go wrong. And as Uber was adding more data centers and cloud providers over time, we knew that this pain was only going to get worse. But in all of this madness, there was a glimmer of hope, which came in the form of M3 Cluster that we've talked some about. And given how well M3 Cluster worked for M3DB, we decided to expand our usage of it. So by 2018, we had retooled all these various components to be discovered and represented using M3 Cluster. So now all of our tiers just had to talk to etcd using M3 Cluster to discover information about itself and its dependencies. M3 Cluster is also heavily used in M3 Aggregator, which is our open source aggregation tier. The aggregation tier is fault tolerant and sharded using the same libraries. It allows for runtime dynamic roll-up and aggregation of user-defined rules that are also stored in etcd using M3 Cluster. And if you're familiar with Prometheus, you can think of this aggregation tier as pretty much just giant distributed fault-tolerant Prometheus roll-up rules. So because we made M3 Cluster generic enough, we were able to apply it to all of our workloads. So this meant that our stateful workloads, such as M3DB, semi-stateful, such as our aggregation tier, which requires a 1 hour warm-up and cooldown during deploys because of the way that we do custom user aggregation, and as well as our pure stateless tiers, they all use these same libraries. So this meant that we were able to write logic once to shard a workload, distribute those shards across failure domains, and weight them on some condition. We could write that once and then just use it everywhere. Also, because there was a single source of truth for the entire state of the world, there was no longer any guessing what build was deployed, guessing what instances were using that build, and trying to reason about what their view of the world might be. There was instead just one source of truth that was stored in etcd that was manipulated and just read using M3 Cluster. And as operators of the system, using M3 Cluster everywhere made it much more manageable. So it no longer felt like we had these various unrelated components with various caveats. Instead, there was just one unifying view of the system as a whole in these placements. And this meant that operations were much easier. So you could replace an entire tier of instances using a single command rather than some coordinated guess and pray deploy. Also, because all of these instances use the same configuration, we could treat them the same. In other words, cattle, not pets. In that you don't want any of these instances to be special or have to treat them individually. And I mentioned this concept of goal state a few times, so let's take a further look at what that means. In M3DB, shard assignments are determined by these placements that we've seen so far, and these sharded assignments are desired topologies that the cluster works to converge on. So the M3DB instances will look at what shards they're supposed to own, look at what data they currently have, and then react to that, and then eventually update the state of the world. So this means that although operations may be imperative, such as add a node, under the hood there actually just changes to this desired state, which makes it much easier for both people or automation to interact with, because although there's these varieties of interfaces to the system, under the hood they're all just influencing change in this declarative way. So more concretely, let's take a look at what it looks like to expand an M3DB cluster using these concepts. So here we have an M3DB cluster with 3 nodes in these various availability zones in a cloud region, and a 4th that we want to add. These nodes are all talking to etcd in which the current placement is stored. And this placement has 4 shards, 3 replicas with the assignment that we see above. So a person or some automation using tooling that's backed by M3 Cluster will come along to add M3DB04 to the cluster. In this case, M3 Cluster will calculate a new placement and store it in etcd, and that placement will say that we want 04 to take over these 2 shards from 03. The database nodes will observe this desired state and work to converge on it by the 4th node streaming the shards from any nodes that own a copy of it. And one really important thing about this is that no matter what external events happen in the system in this time period, it won't affect kind of the steady state of these operations. Like if a node restarts, if they all restart, if someone deploys the cluster, it won't impact this. Like the nodes will just come back up, see what the desired state is, see what their current state is, and work to converge on it. It also means that we can back out of this at any time by just undoing the placement change. So if you just revert the placement change back, then the nodes will stop streaming data and nothing will be deleted. So once the replace finishes, O4 realizes that it has all the data, and then it updates the placement in etcd to reflect its full ownership of the shards. When we first built M3DB, we felt that this approach would make things much easier to automate down the road. So for one, there's a single source of truth for the system, meaning that there is less risk of drift or split brain scenarios, and that all cluster changes were actually just affecting this single source of truth. So comparing that to an imperative approach where you might have to make instance level changes, let the fourth node know that it's taking over some shards, let the other nodes know that it's joining the cluster, there is none of that you have to do. It's just you're changing the single state of the world. Any other external events can happen, and the nodes will just come back up and continue reconciling the state. So to recap, by 2018, we represented the M3 stack using these placements that were driven by M3 cluster. And we had made a lot of progress. Like, we had retooled our entire stack to be more goal state driven, resilient to failures, and we had really simplified a lot of these operations, but many of them, such as replacing a failed instance, still had to be triggered by a person. Of all of these components, M3DB needs the most care to manage since it is a database, unlike those stateless tiers where you can just swap out the entire tier using one command. With the database, you need to wait for data to restream, quorum to be respected, etc. And this is relevant because something else had changed over time, which is that our environment had become much more complex. So whereas in 2016, we had 2 M3DB clusters that we just managed across 2 data centers, by 2018, when we were facing all of these issues, we were managing over 40 clusters across many more data centers and across cloud environments. So what we really wanted was to be able to apply these same concepts of goal state and declarative management that we had at the single component level to the entire cluster or to many clusters. Like, we really needed managing one cluster to require pretty much as much overhead as managing 10. But at the same time, M3DB can only do so much. Like, it's a time series database. If it sees that another node in the cluster has failed, it doesn't know how to provision a new instance to replace it, how to discover information about that instance and add it to the cluster. We really needed to expand the scope of this entire life cycle. And to do that, we decided to build tools for automating M3DB using Kubernetes. So for one, we already had open source users that were using Kubernetes and were using M3DB and wanted a better way to integrate those two and run their M3DB clusters on Kubernetes. In part, M3DB has really tight integrations with Prometheus, and since Prometheus and Kubernetes both play important roles in this cloud-native landscape, we wanted to provide a better integration story for them. Additionally, at Uber, our internal compute team wanted us to experiment with building automation on top of Kubernetes to influence the design of how stateful workloads would be supported on Uber's own internal compute platforms. Some quick information about Kubernetes if you're not super familiar with it. So Kubernetes is a container orchestration system. It runs your containers. It has methods of supporting stateful workloads through persistent storage and other methods, which is really important if you're running a database. And a big part of Kubernetes is that it's self-healing. So if you say that you want 5 copies of your application running and they're currently 0, Kubernetes will start 5. If one of them fails and now there's only 4, Kubernetes will start another one to make sure that there's 5 running. And Kubernetes is also very easy to extend. So there's a concept called CRDs, or custom resource definitions, which allow you to expand the Kubernetes API by adding your own API types to those core definitions. And there's also a pattern of operators, which are custom controllers, and we'll take a look at what that means. Some other relevant things about Kubernetes for our purposes. So in Kubernetes, the base unit of work is called a pod. And a pod is a group of similar containers that are deployed as a single atomic unit. But pods can come and go. So because Kubernetes is self-healing, it may move your pod around in response to things like node failures or resource contention, or maybe even something more intentional, such as your cluster administrator performing a maintenance. So because of this, you're encouraged to treat your pods as ephemeral or otherwise not special. Most of the work in Kubernetes is driven by what are called controllers that implement this observe react model. This is taken from literally the Kubernetes guide to writing controllers, which is an amazing resource. So pretty much controllers are constantly running in these loops. They're checking what is the desired state of the world, what is the current state of the world, and what changes do they have to make to converge on that desired state. And this is a huge part of how Kubernetes managed to be self-healing, because it's just kind of constantly converging on this desired state. So as we were designing how M3DB would work on top of Kubernetes, we began to notice some similarities in their models. So M3DB is goal state driven. It has a single source of truth, which in our case is etcd, and the DB nodes work to converge on this desired state stored in etcd. Kubernetes is also goal state driven. It also has a single source of truth, which happens to be etcd in its case. And these various components or controllers or other actors in the system all work to converge on this desired state. So we got to work and we eventually created our own operator for M3DB. So the operator manages the full lifecycle of clusters that are running on Kubernetes. So actions such as creating clusters, scaling them up or down, performing maintenance operations, pretty much any action that a person would normally have to take, we're able to encapsulate in our operator by leveraging these Kubernetes primitives. And thinking back to earlier, how we were saying that M3DB's scope is only so wide, we were able to expand it by having Kubernetes take care of things like provisioning more instances for us. Using the operator, users can define these higher level states, such as they want some cluster with various parameters, and the operator will in turn take that desired state, translate it into some that it needs from Kubernetes, wait for Kubernetes to converge, and then update M3DB. So let's take a look at what that looks like. Here this is an example of creating a M3DB cluster using the operator. So here a user defines an M3DB cluster that they want to be created. This cluster has some parameters that the user defines, such as they want 1,024 shards, they want 3 copies of each of those shards, they want 9 instances in their cluster, and they want those instances to be evenly distributed across these 3 availability zones in a cloud region. And then the user will submit that desired state to the Kubernetes API, and the operator will pick up on it. In turn, the operator will translate this into some desired state that it needs from Kubernetes. So in this case, the operator will tell Kubernetes that it wants 9 M3DB pods running with these specific parameters. So it wants 3 sets of 3 instances. It wants each of those sets to be pinned to a certain availability zone in a cloud region, and we want them to have some amount of resources that the user asks for. Under the hood, the operator this uses a Kubernetes primitive known as stateful sets, if you're familiar with them. And as the nodes come up, or as the M3DB nodes come up, they'll begin serving the M3DB API, which provides an API around those M3 cluster placement operations that eventually store placements in etcd. But one thing that's important to note is that at this point, there is no M3DB cluster yet because there is no placement. We just happen to have a bunch of containers that are running M3DB that are waiting for work to do. But once the operator observes from Kubernetes that these 9 instances are created and healthy, it can translate those instances into a placement. So using information that we get from the Kubernetes API, such as the isolation group or the availability zone that they're in, the weight of the instance or the amount of memory that it has allocated to it, the addresses it's serving requests on, etc., the operator can translate that into a placement, submit it to the M3DB API that's running on these nodes, and then they'll work to converge on it. So in this case, they'll just communicate with each other, notice that it's a new cluster, that there's no data to be had that there's no data to stream because it's a new cluster, and eventually they'll converge by just updating their actual state in the M3DB API to reflect that they're all available. So although we've only shown what it looks like to create a cluster, the operator handles day-to-day operations and makes them a lot easier. So for example, when scaling an M3DB cluster, you normally have to add nodes one by one and wait for them to totally join. But with the operator, you can just say that you can say something like double the size of your cluster and go get some coffee, and the operator will translate that into these intermediate steps such as provision one more instance, wait for it to be available, provision the next instance, et cetera. So it kind of translates this higher level state that you want into these intermediate steps. The operator also takes care of replacing failed instances or updating cluster configuration as the user's configuration of the cluster changes. And one thing that's really nice is that these operations all follow the same pattern. So they just look at the desired state of these various systems, look at what the current state is, decide what needs to change, and affect that change using these APIs. And this makes the tooling a lot easier to understand because it all follows the same pattern. So building our operator was a pretty positive experience, and we have open source users that are running it in production today. And we think that a few factors contributed to its success. So a big part of it was that it sat between these two goal state driven APIs that are kind of both designed in ways to prevent you from shooting yourself in the foot when building automation. So for example, Kubernetes will prevent you from accidentally deleting more than one instance because you're not saying, okay, delete this instance, delete this one. You're just affecting how many you want running in total. Similarly, M3DB will prevent you from removing more instances than you want using similar primitives. And thinking back to earlier how we were saying that during these state changes, any external events can happen to the cluster, such as the cluster, nodes can restart, they can be deployed. The operator works the same way. Like it can be shut down for hours or days, and even in the meantime, like things in the state of the world can change. And when the operator comes back, it will just continue reconciling the overall desired state by comparing what is desired and what is current. Similarly, you can have 2 copies of the operator running or 10 copies running, and they won't conflict with each other because of the way these APIs are designed. And when we think about, again, how we said M3DB's scope is only so wide, we need to expand it. Part of the reason that we were able to do that is that M3DB and Kubernetes share similar concepts. So for example, M3DB has these failure domains that influence shard placement. Kubernetes has the concept of failure domains in these scheduling constraints so that you can say that you need instances specifically running in one availability zone or under some other constraints. Similarly, where M3DB tracks how many resources an instance has to affect the weight of the instance, Kubernetes can provide us that information by letting us know how much memory is allocated to a container or how large the disk attached to it is. So looking back on our experience getting M3 to where it is today, we think there are a few things that really helped. So for one, finding these common abstractions that would apply to all of our workloads made the mental model of the system much easier and made reasoning about it easier. So by applying these placements to everything, we were able to kind of unify these previously fragmented systems. This is also a great efficiency gain by being able to apply best practices such as weighting and fault tolerance everywhere, even if we might not have previously explicitly built it in. Additionally, by making these abstractions goal state driven, we made the system much easier to operate because we didn't have to worry about these external events affecting the steady state. And this goes a long way towards this idea of being self-healing. And when it came to making M3DB run on Kubernetes, we found that it was much easier because we had embraced some of these Kubernetes principles in our own system. So for example, where Kubernetes encourages you to treat pods as ephemeral and subject to being moved around, we kind of embrace this by having quorum reads and writes of all the data and by having fault tolerance that in accordance with these failure domains. Also, at any point in time, if M3DB encounters a disruption, when it comes back, it just continues gracefully resuming the work that it was supposed to do by checking etcd. So if Kubernetes moves us around, then again, when the container comes back up, it just continues checking what it's supposed to be doing. And all of this kind of goes hand in hand with this idea of treating our instances as cattle, not pets. Like, we no longer had to operate on instances directly or worry about anything on an instance level because of this. So some things to consider if you're thinking about using Kubernetes or any other orchestration system for your workloads, especially stateful ones. I think the biggest thing is that any orchestration system is going to imply some complexity, and Kubernetes is definitely no different. Kubernetes is a really powerful system with a lot of features, but with that kind of comes more things that you have to keep in your head and reason about. So I think you have to take into account your own context. Like, is this complexity worth it? And what are the benefits that you will get from it? When you get to the point of just the number of clusters that you're operating or the number of instances of your application that you're operating being a bottleneck, then maybe by paying down some of that complexity and by building tooling for it, that's helpful. And you kind of have to take into account some of these things that go along with Kubernetes, such as how will your system respond to failures? If Kubernetes decides that there's resource contention on the node that you're scheduled on and that it has to move your container around in response to that, will your application still be okay, or will your database still be okay? So maybe this isn't a special fit if you have, say, super special instances of your application running that you need to always be running except under catastrophic scenarios such as a hardware failure or something else completely out of your control. Maybe in that case, it's not a great fit. Or maybe you need to kind of redesign how that works. But in our case, since M3DB was able to tolerate these failures, the cost benefit there was worth it. Additionally, consider that the requirements and the guarantees of your system are going to greatly influence the requirements that you need from your tooling and your automation. So, for example, in our case, because we wanted to provide strongly consistent reads and writes, it made it much easier to offload some of that work to etcd and leverage etcd for this use case. But using etcd or using some strongly consistent system might be a heavy-handed approach for a lot of applications. Like, maybe you just eventually need some number of instances of your application running, so those requirements kind of influence each other. So to recap, by building these common abstractions for all of our workloads, we're able to make the mental model of the system much more manageable. By having these abstractions follow a goal state-driven approach, we are able to make the system much more friendly to automation by these variety of interfaces for kind of influencing change. And then when it came to actually automating the system using Kubernetes, it was much easier because we were pretty closely aligned with some of these Kubernetes principles. That's about it. Here are some links where you can check out all the things that we've talked about. All of this is open source except for the Uber internal stack or whatever, but we run the same exact code that you see here. So M3DB, M3 cluster, our aggregator. We also have some docs that are a good place to start. And please leave feedback on the O'Reilly site if you have some time. That's about it. Thank you. And then, we have some time for questions if anyone has them.
Hi. So I have a lot of questions. Okay. So first, have you tried using GitOps instead of the source of truth in Git instead of that?
So I think that the GitOps approach kind of is made easier once you have Kubernetes providing this control plane. For example, we manage our clusters in configuration. So these clusters, such as how many instances you want, like those are managed with Git. But when it came to actually automating the instances, we kind of needed the control plane to take in that GitOps backed information.
Then you can have like some sort of another controller that listens to Git and apply.
Sorry, can you elaborate?
Never mind, we can talk about after.
Okay. You probably mentioned this. What's the relationship between shards and instances? So an instance has some of the shards?
Yeah.
Yeah.
So although that one example we saw where the placement only had 4 shards, for example, in our production workloads, we'll have 4096 or 1892 shards, and instances will own, like when the cluster is small and we're starting with a new cluster, they'll own a lot of those shards. As we expand the cluster, they'll all own fewer and fewer shards. But yeah, the idea is that they own some small subset.
What's in front of the instances that chooses which instance to go to?
The question was what's in front of the instance that chooses which instance to go to. So we actually implement all of that in our libraries. Like we don't have, or at least we currently don't have, say, like a proxy in front of them or something. So part of that is because all of the entire stack is based in Go, that we can kind of just leverage these same libraries. But we have another thing called M3 message, which is reliable like message redelivery. And that uses that, or like those are the routing libraries that we use for everything.
Hi, Cassandra's obviously not sitting still. Have you like kept on top of or maintained a relationship with Cassandra to give them input on what was failing, and have you seen progress on them that they have made improvements that might have solved some of your issues?
Yeah. So we had a tight relationship with DataStax back when we ran a Cassandra-based stack for support and kind of advice. I really think it just came down to this completely different use case. Like I think at the time, at least, I don't know if they have now, like although Cassandra has DTCS for like time series or for like time-based compaction, they don't have, or at least at the time, they didn't have like that time series encoding kind of like at the data layer, which was kind of crazy. It was like, we were storing like 2 64-bit values for the time and the value of like every single metric pair, when those could be like that much more if we just used kind of purpose-built compression. I haven't caught up, or I haven't kept up with what the current state of if they're supporting that today is. But yeah, I think it was just kind of a difference in use case.
Okay. So how do you back up etcd itself? And when?
Yeah. So our etcd nodes take backups every couple hours. Huh?
By themselves?
Yeah. All right. It's kind of crazy. But so we have a cron on all of our etcd hosts that takes the most recent snapshot and copies it to another directory. So our like model there is that we assume that we won't lose all the disks in the etcd cluster at once, and that one of them will remain healthy. But yeah, we don't have like a offline backup strategy.
So follow up here, I understand how you had some cluster intelligence that was orchestrating all of these moves, and you've moved over to an operator. Other than simplifying your stack and aligning with cloud native offerings, what benefits have you gotten from this move?
So let me elaborate on what the previous method was. The previous method was people. Like you would get a page that said, this host is down, and then you would have to provision a new replacement host, and then you would have to run a CLI command that said replace this host with that host.
So you had none of the automation?
No.
Okay.
Yeah.
Got it.
Okay. So Kubernetes itself come with etcd. Are you using the same database, or you have your own etcd instance?
Yeah, we have our own etcd instance. Mainly because we just have we don't tune it like differently with different auto compaction and max database or max key value size based on certain things. So we figured just use our own.
Okay, and is this like a fork of the open source etcd, or is this?
Oh no, this is vanilla etcd. It's just M3 cluster is kind of the libraries that read and manipulate the data that's stored in etcd. So for example, like when you're doing a placement update, we use etcd's like version control to make sure that 2 instances don't say like conflict on a placement update. And if one of them gets a conflict, it'll re-reconcile its state and decide if it actually needs to make that change or not.
Okay, but you store the CRD objects inside Kubernetes etcd. I see.
Yeah. So yeah, we store the Kubernetes objects in Kubernetes etcd, and then the M3 cluster-based data in our own etcd. Also, part of this is because like if you're running on a managed platform such as GKE, like you don't have access to their etcd. They abstract that behind their control plane, so we needed our own anyway. Sorry?
I was wondering, so you have your own M3 collector, and that looked an awful lot like a Kubernetes controller. How come you didn't just fully embrace that into a Kubernetes controller to manage the nodes after Kubernetes allocates the nodes and provisions them for you? Like, you had Kubernetes does the provisioning, and then you did the actual like database work was still kind of custom on its side. Why not embrace that more with like a CRD or a custom controller in Kubernetes?
So the collector is more just like the metrics daemon that hosts send their local metrics to. So we don't have like super specific requirements around that, other than that there is one running on the host. I don't know if we.
Not the collector, the controller, the M3 controller, my mistake.
So the operator itself is just deployed using like a static YAML manifest, and then it installs the CRD type, and then the users like create objects with that CRD type. I might not totally be following what you're saying, but we can chat after as well.
Okay, so how do you create a new instance? I assume that a new instance is like a new VM or a new machine, right? Do you use Terraform or something like that?
Within Uber's data centers, we use Uber's like internal hardware management stack. In our cloud zones, we use the cloud providers' respective offerings.
Have you tried using Terraform for that?
So we use Terraform to manage our Kubernetes clusters in the cloud regions. But yeah, like Uber's internal provisioning systems don't have any Terraform backed, or don't have any like Terraform implementation. Cool, I think it's about it. All right, thank you all for your time.